In Part 7, I focused on the discussion regarding the most common acids used in chemical assay. Included were the concentrations commonly used and purchased. The more concentrated the acid, the cost is less in the long run, due to diluting the concentrated to the required concentration needed. In this presentation, I want to focus on sample decomposition. There are some important considerations on how this can be achieved. I'm Rob Boyko, Boyko Mineral Exploration, and welcome back. Sample preparation is a big challenge. The samples collected, such as soil samples, will be of unknown chemistry or mineralogy. These may also be rock chips or core drillings. The samples that you take from the field, are they representative? There is no real way of knowing. It takes a lot of sampling to determine if they are. More important, are you going to be able to fully dissolve your samples? Chances are that you will be separating your samples into multiple samples for quantitative and qualitative analysis, as was shown in parts 1 to 4 of this series. Will your samples be adequate in regards to separation and isolation of the analyte in question, that is, of interest? If you are going to be using instrumentation for analysis, then all your samples will need to be in solution. The only exception is with XRD and XRF analysis. These samples are usually compressed into hard disks or fused into glassy ones. The overall objective is to be able to dissolve your sample completely in order to obtain a homogenized aqueous solution for subsequent separation and isolation of the analyte to be assayed, that is, to be analyzed for mineral concentration. Sample preparation is based on sound chemical and physical principles. The choice of reagents, the reaction vessel such as a test tube or a beaker, and the temperature profiles of the samples to be digested will establish the reaction kinetics and the mechanisms for the reactions to take place. Kinetics is the driving force that permits the total dissolution of a sample. This includes processes such as reducible extraction of elements, the solubility of an analyte in the sample, its volatility to heat, as well as the stability of the analyte in a solution. There is also a safety aspect in regards to a chemical reaction. This is all based on the type, concentration, and amount of acid or acids to be used, the rate of which the sample matrices dissolve, and the method of dissolvement. That is to say, will it be a wet-dry process which utilizes fusion in the process, or some other method or procedure? Some sample material cannot be fully decomposed by a cool acid alone. To increase the reaction, a form of thermal excitation will be required. This is simply achieved by heating the sample that is placed into a solution. The apparatus used is not much more than a simple single hot plate. However, when it comes to refractory type materials or samples that resist dissolvement, a wet-dry system is usually involved or employed. This consists of melting the sample with an added flux, then pouring it into a disc mold, cooling the disc, and placing it into an acid bath to fully dissolve the fusion cake. There are very few silicates that are water soluble. This wet-dry method may be utilized to break down those chemical bonds that form the crystalline structures of the sample material. The dissolving of sample material is carried out using two systems, an open system and a closed system. In the open system, the material that is to be dissolved is done in a test tube or a beaker that is open to the atmosphere. A closed system is a system where the container that holds the material to be dissolved is sealed to the atmosphere. During dissolvement, the system may become pressurized as it is being heated. Special containers used for this purpose are commonly referred to as par bombs. There are some containers that are purposely manufactured for microwave heating. Most manufacturers have their own systems for heating par bombs. Most reagents that are used for dissolvement of samples use an oxidation reduction chemical process, which leaves the analyte in a more stable form. Total decomposition is related to the mineralogy of the sample and its related chemistry, which in turn will determine the appropriate method of dissolution. Rocks, concentrates, soil samples, and others will have varying compositions. There is no one single procedure that will apply to every sample. The decomposition of a sample may require total dissolvement, as with an instrumental analysis, using ICP-MS as an example, which just stands for intercoupled plasma mass spectroscopy. Now, a partial dissolvement may be needed for analyte separation. Others will require a selective dissolvement to isolate the specific analyte. Some samples may need to be attacked using more than one method, such as a two-acid or a multi-acid attack, or using a wet-dry system of fusion, then followed with an acid. In order to summarize, that is, to put things into perspective, for dissolving sample material, the nature of the sample must be understood. Does the sample contain copper or more than one element of interest? Is the matrix of the sample a silicate such as quartz? How will the reaction with acids react on the sample matrix and the analyte? Most of the time you will want to fully decompose your sample material into a solution. How effective will your technique or choice of dissolvement be? Will there be any interferences from the reagent that you are going to use? More on interference in a later presentation. But for now, will there be any unwanted contamination of your sample, either from the reagent itself or from the equipment that you will use to dissolve the sample in? Optimization is a term used to define how one will dissolve the sample to create the required solution. The limit of detection is important. The solution's concentration of an analyte must be within a range. If the concentration of analyte is too small, it may not be detected by either an instrumentation or by titration. Maximum range is another issue. If concentration is too large, it may overload the system, giving a false analysis. And of course, safety is a big concern, especially if one was to use microwave heating or a closed system approach to dissolution. Then there is economics. Will your analysis cost too much? Not to mention the disposal of dangerous goods. In regards to dissolving your sample, you need to consider a few items, some of which have already been discussed, but worth re-mentioning. The nature of the sample is the first, including its matrix, such as arsenopyrite, chalcopyrite, or wolframite, and so on. You see, you need to identify the analyte of interest. Now, wolframite, as an example, will be a complex containing iron, manganese, and tungsten with quartz and pyrite. You will need to determine its solubility with solutions in regards to the elements of interest and the matrix. By determining the aforementioned, you can determine the type of analysis that you may require, such as titration, which will be discussed later in this series, or instrumental. You will also need to determine if there will be any sample loss due to volatilization, etc. Contamination is another factor. Remember that acidic solutions are used to dissolve basic sample material. That is in regards to chemistry and chemical acid-base reactions. Basic solutions are used to dissolve acidic samples. Oxidizing reagents such as nitric acid are used to reduce samples using redox reaction principles, whereas reducing agents are used to oxidize samples. The goal in dissolving samples is to create soluble salts and other ions present within a sample that can be easily solubilized in a solution. Some of your samples will contain organic substances, especially in soil samples. Organics can be dissolved using an organic solvent, such as acetone, ethanol, ethyl acetate, diethyl ether, and others like toluene or benzene. Now, dry oxidation is normally referred to as ignition for the removal of organic material. This is when the material is burned to an ash, then dissolved using a suitable acid. Dissolving a sample with an oxidizing acid such as sulfuric acid or nitric acid and adding a catalyst like copper or selenium is called wet oxidation. Another method that is used is opening out. Now this term refers to fusion. High heat and a flux are used to reduce the melting point of a sample, which in turn creates a fluid molten solution. And then when cooled, the remaining fusion cake is then acid digested. The term sintering is just a way to describe the method of heating a sample just before or just below its melting point. 4 factors determine decomposition. The smaller the particle size, the larger the surface area of the sample. This results in more surface area for an acid to attack. Temperature increase allows for a more rapid decomposition due to a greater thermal agitation of the molecules. The larger the sample size indicates a larger amount of reagent to be used, which in turn increases the length of time it takes to decompose the sample. The amount and the concentration of the acid or base solution will also determine the rate of decomposition and the efficiency of the solution to attack the sample. Now caution, never allow your reactions to become arrested. That is, to stop reaction decomposition or cause unwanted precipitation. A couple of examples is apatite. Now apatite is composed of calcium phosphate. Adding phosphoric acid will produce calcium hydrogen phosphate, which is not soluble. Now adding sulfuric acid to limestone, for example, results in calcium sulfate, which is also not soluble. There are several methods of decomposing samples into a solution. The 4 most common involves acids, fusion, sintering, and by special methods being par bombs and microwave heating. Each of these methods will be discussed in the next few slides. Chemists like to describe dissolution in terms of digestive range. The term pseudo-total refers to a total dissolvement of a sample. Partial is similar to selective. Partial refers to a partial dissolvement of material. Now this partial dissolvement was demonstrated in parts 1 to 4 of this series, which focused on qualitative analysis, where we separated the sample into groups of elements. Selective refers to the selective separation of an analyte. It was shown that lead in the group 1 solution could be separated from the soluble matrix by boiling the solution, leaving the silver and the mercury as a residue. The method of breaking down a sample could utilize a room temperature acid, referred to as cold extraction, or the solution may be heated to facilitate the decomposition faster. Agitation can be achieved just by stirring with a glass stirring rod, shaking, or using a stir plate and a magnetic stirring rod as shown. The method used may incorporate any combination of. Now microwave heating and bomb decomposition will be addressed later in this presentation. Most acids will produce salts. There is an exception, and that is sulfuric acid. Hydrochloric acid produces chlorides, and nitric acid will form nitrates. Now sulfuric acid, which is an oxidizing reagent, produces sulfates. Perchloric acid, which is a very strong oxidizer, forms perchlorates. Hydrofluoric acid results in fluorides, and orthophosphoric acid generates phosphates, as well as complex phosphates. This picture was uploaded to Google Images by Zana Chase. It's a good representation of a 4-acid decomposition schema. The term 4-acid simply means multi-acid. It starts by preparing the sample using concentrated hydrochloric acid to decompose the carbonates. The nitric acid and hydrofluoric acid are added to the solution to solubilize the silicates and others. Additional nitric acid is added to remove the fluorides. Silicates will be lost. Additional nitric acid is added and heated for 24 hours to ensure total decomposition. The solution is then placed into an intercoupled plasma mass spectrometer for analysis. Okay, the takeaway here is that a single acid may not fully dissolve a sample. Using aqua regia, which is actually a 2-acid digestion, aqua regia will dissolve the sulfides and most of the metal oxides, but not all of them. Now this is the same in regards to hydroxides and some of the carbonates. Therefore, this method is well suited for certain rock types, soils and sediments. The acids which are commonly used for multi-acid decomposition is nitric acid, hydrochloric acid, hydrofluoric acid, and perchloric acid. At times, sulfuric acid may be used. Silicates are dissolved using a combination of hydrofluoric acid along with nitric acid and perchloric acid. However, during evaporation, the silica will be lost as silicon tetrafluoride gas. Now, a multi-acid digestion will not fully dissolve the sample if there are refractory or resistant minerals present. Examples would be barium in barite, chromium in chromite, titanium in rutile, tin in cassiterite, aluminum in corundum, and of course rare earth metals in monzonite. Antimony, arsenic, boron, and selenium, and as mentioned, silicon may be lost during decomposition, especially when the sample solution is evaporated to dryness. Hydrofluoric acid will form fluorides. Fluorides are not soluble in other acids such as hydrochloric acid. By using nitric acid will help solubilize the fluorides for removal. There are advantages to chemical decomposition for quantitative analysis. The first, that it is a simple procedure. All it takes is to pulverize the sample to a fine powder and add a little acid. Sample size per test is small. Equipment cost is lower than microwave, bomb digestion, or XRF equipment for that matter. Using high purity reagents contain very low levels of contaminants. This allows for the creation of high quality blank samples. More on blanks in an upcoming presentation within the series. The low dilution ratios, that is, between the sample and the acidic solution, allows for a lower detection limit in regards to elemental concentration. Solutions are used in instrumentation analysis. Instrumentation uses a process that requires the solution to be subjected to flame nebulization and/or plasma excitation. Salt content is very low in an acid solution. Salts will interfere with the analysis. The low salt content allows for a more stable nebulization in flame and plasma processes as it reduces the likelihood of the salts plugging up the nebulizers. Instrumentation is beyond the scope of this series and therefore is only mentioned. There are a few disadvantages to acid digestion without using special techniques, which will be discussed in a future presentation within this series. Refractory or resistant minerals, such as chromite, zirconium, and others, will not decompose. Some will only partially decompose. Other elements may be volatilized, while others may be lost during fuming. Because of these disadvantages, multi-acid digestion may not, or in some cases, be suitable for major elemental analysis of rock samples. Throughout the series, I occasionally mentioned the grade of a reagent as being ACS. In the next few slides, I will be discussing the different grades. Reagent grades are the quality assurance properties of the reagents. As shown, circled in red, it reads reagent ACS. These chemicals will have their contaminants and their concentrations listed on the packaging or labels. These chemicals are of the highest in purity and the lowest in contamination. That is why they are the most commonly used grades for inorganic analysis, especially in the mining industry and assay laboratories. These chemicals meet the minimum purity standards laid out by the American Chemical Society. Hence the term reagent, ACS, or simply ACS grade. Reagent grade chemicals, such as that shown and circled in red, may not have the contaminants and their concentration shown on their labels or on the packaging. One may have to contact the manufacturer or supplier. The purity of the product may be equal to or slightly less than an ACS grade of reagent. It is the manufacturer that sets the standard for this product, not the American Chemical Society. CP grade simply stands for chemically pure. This grade of chemical is primarily used for medicinal compounding by pharmacists. It meets the pharmacopoeia requirements in the National Formulary. The Pharmacopoeia is an official book describing medicines and/or other pharmacological substances. The National Formulary is a pharmacopoeia, or a list of available drugs, particularly prescription drugs. This grade of chemical is a lower grade of chemical compared to the ACS grade or reagent grade of chemicals. USP simply stands for the United States Pharmacopoeia and National Formulary. This grade of chemical may not be useful or even adequate for use in analytical analysis. For qualitative analysis, it may be adequate, but contamination and lack of purity may skew the results. This grade can be considered as a lower grade of chemicals compared to the CP grade of chemicals. NF, by itself, stands for the National Formulary. Now, this grade of chemical also may not be useful as a reagent for analytics. One would need to check the National Formulary list of chemicals to determine if the chemical to be used for a test or experiment will be adequate. This grade may be useful for qualitative analysis if the intent is to identify an element instead of an element's concentration. The purified grade simply means that the chemical is physically clean and of good quality. However, it does not meet the ACS, reagent, USP, or CP grade standards of chemicals. This grade of chemical is primarily used for industrial applications, not usually used for any type of assay experiment. Its purity can range from 70 to 95% and is not usually listed on the packaging or label. Due to its low purity values, the use of technical grade chemicals will normally never be used for assay analysis of any type. SPECTRA is an acronym which stands for Spectrophotometric Grade, or simply SPEC grade. The bottles normally do not have spectra on their labels, but have reagent, ACS, listed. This designation is given to organic solvents that are used in infrared spectroscopy. These chemicals are equal to ACS or reagent standards. These are of the purest organic solvents. HPLC is the acronym for High Performance Liquid Chromatography. It is a designation also given to organic solvents. These solvents are specifically prepared for chromatographic analysis. Now, as a side note, any analysis or experiment that you may wish to conduct will only be as good as the sample that you will have and the reagents that you choose to use. If possible, always try to limit yourself to using ACS grade of chemicals. By doing so, you limit the errors that results from the contamination and poor purity that may be associated with the chemicals to be used. Well, this concludes part 8 of this series. In this presentation, I wanted to focus on sample decomposition. I discussed some of the important considerations and how this can be achieved. I also expanded on the different grades given to the reagents that are used. In the next presentation, which will be part 9 of this series, I will be focusing on the dry part of wet-dry composition. I hope that you found this presentation helpful and at least informative, and hope that it entices you to view part 9 when it is published. If you found this presentation informative, or you know of someone who would benefit from this education series, please give it a thumbs up, a like, and a share. It's my only reward. I am Rob Boyko, Boyko Mineral Exploration, and I thank you for watching.